All right, let's talk about graphing logarithmic functions. So in this part, we are asked to graph the function f of x equals log base 2 of x. Typically, when we are graphing something, I usually advise you to go ahead and make an xy table. But this is a little bit more challenging to do. So if I don't pick very specific x values in here, it makes this problem very challenging without a calculator. So I'm going to assume this is something that maybe we don't have a calculator. So if I were trying to plug in something like -3, for instance, I would try to do log base 2 of -3. Well, you're asking 2 to what power is -3? That's something that I don't know without a calculator. So instead of doing it this way, I would recommend rethinking this function, which instead of f of x, maybe if we write it as y equals log base 2 of x. If we can rewrite this in exponential form, it's going to make creating our table a little bit easier. So if y equals log base 2 of x, we would know that 2 to the y power equals x. We're used to saying, okay, fill in x, plug it in, and then that's going to give us our y. But no one says that you have to fill out the x column first. So what if we were to plug in numbers for y and then solve for x? So 2 to what power? That would be our y, whatever we want 2 to be raised to the power of. So I could say 2 to the -2nd power. If I plug -2 in for y, well, that's 1 over 2 squared, or 1/4. Now we have a point for this logarithmic function. If I plugged -1 into y, 2 to the -1st power is the same as 1 over 2 to the 1st power, or 1/2. If I plug in 0 for y, 2 to the 0 power is 1. If I plug in 1, 2 to the 1st power is 2. And if I plug in 2, 2 to the 1st power is 4. I could even plug in 3 because that'd be a point that's going to fit on this graph. 2 cubed is 8. Now, I still want to plot these points like typical points, x comma y. I'm not going to flip-flop them. So if I plot 1/4 -2, I go to the right 1/4 and down to -2, and we plot a point. 1/2, oops, my pen is stuck. Let me try that one again. 1/4 -2, we'd have 1/2 -1 would be a point here. 1, 0, 2, 1, 1, 2, 3, 4, 2, and then 8, 3. So here would be our function f of x, which is a logarithmic function. And we've already done an example like this before, where we basically, talked about if we had the exponential function that looks something like this, then we can get the logarithmic function by reflecting it over that line y equals x. And then we get the logarithmic function to look something like this. The exponential function had a domain that was all real numbers. So in this case, our logarithmic function, which is the inverse of that, would have a range that was all real numbers. So the range for f of x here is going to be all reals. On your inverse function, you would have a range that would go from 0 to infinity because you would have had a horizontal asymptote here at y equals 0. So if you're going to take the inverse, then instead of y equals 0, you would have an asymptote at x equals 0. It's going to be vertical. So here we have a vertical asymptote at x equals 0. And your domain, since the range of the inverse function was 0 to infinity, that becomes the domain of your inverse. So that's going to be 0 to infinity here. And this is going to be the case for all logarithmic functions of the form log base a to the x power without any types of transformations, where you have an a value that, all the restrictions that we've talked about before, a can't be negative, that type of thing. So if we want to take this a step further and take something that, yes, we had log base 2 of x, but now we're taking the log base 2 of, in this case, x minus 7, or x plus 2 and then adding 4 outside of it, or taking log base 2 of negative x, or the opposite of log base 2. So all of these are transformations of the original function y equals log base 2 of x. So something that I'm going to do that's going to make this a little bit easier, I'm actually going to copy this table to the next page so that we can reference it as we are talking, through these problems here. So just remember that this was our original function, and we're going to utilize that table to do these transformations. So let's talk about this first one. We want to figure out how does it compare to the graph. We want to write a table for each. Where would the asymptote be? What's the domain? And then what's the range? So for this function, f of x equals log base 2 of the quantity x minus 7. If you're subtracting 7 from x inside these parentheses, that means that we're going to be moving the points right 7. So we'd essentially be taking this entire graph, moving it all right 7 points. So when you move something to the right, what that means for your table is you are going to be adding 7 to the x coordinate, right? If we were to take this point right here and move it to the right 7, instead of it being 1, 0, it's going to be over here at 8, 0. So you're adding 7 to the x column. So all we have to do is take our original table for y equals log base 2 of x and add 7 to your x column, but keep your y column the same. So this would be 7 1/4, comma, -2 for your first point. 7 1/2, -1. 8, 0. 9, 1. 4 plus 7, that's going to be 11, 2. And then 8 plus 7, that would be 15, 3. So all of these we're able to go through and just adjust based on how the graph is actually going to move. So if the original graph looked like this, the original graph had an asymptote at x equals 0, right here on the y-axis. So if we were to shift it over 7, that means our new asymptote is over here at x equals 7. And that's going to impact our domain. Our domain is now going to go from 7 to infinity because it's over here. But our range is not going to be impacted. That's still going to be all real numbers. So we don't necessarily have to graph it. We weren't asked to, but being able to compare it back to the original is a big part of this. So the next one, f of x equals log base 2 of x plus 2, and then that's in parentheses, and then we have the plus 4 out here. This means that we're going to take from the original function over here in the red, we're going to move it left 2 and then up 4. So left 2 means that we need to subtract 2 from all of our x coordinates, and up 4 means we're going to add 4 to all of the y's. So if we subtract 2 from -1/4, we would have 1/4, or -2 plus 1/4, that's -1 3/4. Subtracting 2 from 1/2, that's going to be -1 1/2. 1 minus 2 is -1. 2 minus 2 is 0. 4 minus 2 is 2. 8 minus 2 is 6. And then for our y's, we want to be able to move it up 4, so that means adding 4. So -2 plus 4 is 2, and we're going to go down the line 2, 3, 4, 5, 6, and 7. So again, picturing this, our original log base 2 of x looked like this. If we're going to move it left 2 and up 4, we're taking that vertical asymptote, and now it's going to be over here at -2. So our asymptote is going to be at x equals -2, which then impacts our domain. I'm sorry, I wrote range, but I meant to say domain. So it's going to impact our domain and say that our domain goes from -2 to infinity because it's going to be over here, but up 4. So it's going to be something like this. So our domain will go from -2 to infinity, but our range is still going to be all real numbers. So the biggest thing is just recognizing what do each of these things do. So the negative, if you're multiplying a -1 in front of the logarithm, this is going to be a reflection over the x-axis. Versus if the negative is being multiplied in front of the x alone inside of the parentheses, this is also a reflection, but this one's going to be over the y-axis. So I want you to picture both of these and how that works. If you're going to reflect over the x-axis, right? If you take this point, for instance, and reflect it over the x-axis, it's going to end up down here. So the only difference is your y-coordinate is now the opposite of what it was. You don't want to say it's negative because what was negative is going to become positive. So it's the opposite of what it was. So in this case, we would want to take for our table, you would keep all of the x's the same. So 1/4, 1/2, 1, 2, 4, and 8. But all of the y's will become the opposites of what they were. So this would become 2, 1, 0, -1, -2, and -3. Versus over here, reflecting over the y-axis is going to make all of your x's the opposite. So you would have -1/4, -1/2, -1, -2, let me move this, -4, and -8, but you would keep all of the original y's. So -2, -1, 0, 1, 2, and 3. So then to answer what's going to happen with your domain and range and all of that, well, if this is your original function, if you reflect it over the x-axis, remember that you have this horizontal, or I'm sorry, not horizontal, I'm drawing from exponential. You have this vertical asymptote right along the y-axis. So if you're reflecting over the x-axis, you're not changing its location. So your asymptote is still going to be x equals 0, and therefore your domain and range aren't going to be impacted. Your domain will still go from 0 to infinity, and your range will go from -infinity to infinity. But in this case over here, if this was your original log base 2 of x, if you reflect over the y-axis, it's going this way. Now, that's not going to impact your asymptote. It's still going to be x equals 0, but that is going to impact your domain. Instead of it going from 0 to infinity, it's now going to go from -infinity to 0. And then your range will still be all real numbers.